I want to take a look at this question that says a nonlinear spring is tested by having a 170 pound cylinder impact with it with a speed of 10 feet per second. The spring resistance is shown in the accompanying graph. Determine the maximum deflection of the spring with and without the nonlinear term present. Answer in inches. There are two ways to approach this question. One is convert the deflection into inches while working with it in feet. The other option is put everything into inches and then get inches directly. I would do everything in inches in this video. Here we go. So first we'll write the given and required. I know that the weight force is 170 pound force. Gravity is 32.2 feet per second squared. V naught is 10 feet per second squared. V final, which I'll call V2, is 0 because at maximum deflection, there's no speed. I'll also define H2 as well as H1 for gravitational potential energies. H2 is what I define 0. H1 is pretty much at X because if you look at this graph, it starts at the impact point, which is the equilibrium height of the spring. At maximum deflection, you've basically traveled a distance of X in inches. So if I define the maximum deflection point as my datum, then technically my H2 would just have a positive X. Okay. Now we have our given and required. Givens, we want to find X basically. So what is X in inches? Let's move on to our analysis. We observed no non-conservative forces, no non-conservative forces. Therefore, we will assume that energy is conserved, which enable us to use this lovely formula. Work done by non-conservative forces is equal to the change in potential energy plus the change in kinetic energy. I wrote that backward, but it's fine. That's the change in kinetic energy. This is the change in potential energy. And we know that the work done by non-conservative is 0. That will equal to half mv squared plus the gravitational potential and the elastic potential, which you can define as the weight force times H2 and the weight force times H1 plus the change in the elastic potential energy. I cannot use the formula half kx squared for my elastic potential energy because my spring is not linear. That means we need to go to something more fundamental. We know that energy, let's write this down in a box. Energy, or call it work, is force dot distance traveled. And if we integrate force dot distance traveled, we will get, that's d work by the way, we'll get the work done. So we have force as a function of deflection in inches, which is convenient So we will simply integrate it to get the work done by the elastic potential energy. I mean the spring. So drop everything down. We take the integral from no deflection to the maximum deflection x, which is in inches. That is equal to 16x squared plus 449x dx. Now we will plug in some numbers and evaluate the integral. So we define that v2 has no speed. That term goes to 0. h2 has no height, so that goes to 0. We are left with 1/2 mv, change that to naught, mv naught squared minus weight times h1 plus 16x cubed over 3 plus 449x squared over 2. Now I want to note on the units of each of these terms. This term, and this collection. M is in pound mass. V squared is feet per second squared. Together, this will give me pound force times foot. Now this term, I have weight as pound force times h in inches, which technically this is x. I didn't plug that in correctly. And here we have pound force times inches. So I'm left with this one term here that doesn't fit in all together with the rest of the stuff. So I will simply convert that by multiplying by 12 inches per feet, and everything will be good. Okay. Let's plug in more numbers. Whoops. I have -6. M is 175 pound force divided by 32.2 foot per squared second. And then mine is 170 pound force multiplied by x plus 16 over 3 x cubed plus 449.9 over 2 x squared. As you see over here, we have a cubic equation. You can either go plug this into your calculator or the cubic formula and solve for x. But in this video, we'll do it in a simpler way. We'll plug into decimals and find the x-intercept, assuming this is f of x. Let me pull up decimals. Okay. We have f of x equal to -6 times 170 over 32.2 minus 170x, and then plus 16 over 3 x cubed, and 449 x squared over 2. Now if I look at the x-intercept, wait, let's double check that. Yeah, I'm missing something. 1 second. I forgot v squared in this equation. That's 10 squared. Here we go. Again. 10 squared. Okay, now if we look at the x-intercept, we'll get 3.95418. X equals 3.59. Let's double check that. Oh, 954. 95418. And x is in inches. So this is our first answer. Notice that there are 3 x-intercepts on this graph if I zoom out enough. Sorry, 2. The other one over here would technically be the spring stretched out itself instead of being compressed. So we want to take an x that's above 0. Okay, part 2. What happened if we take away the nonlinear term? And then the equation becomes easier. But for consistency, we'll still use the equation that we developed over here, but just take away the nonlinear term. So we still have 0 equal to 6 times 170 over 32.2 times 10 squared minus 170x. But this time I don't want the cube root, I mean the x cubed term. I would just plus 449 over 2 x squared. Now we solve this quadratic equation, and we can either do that through negative b plus minus b squared minus b 4ac over 2a, or we can go back to decimals, which I have over here, and then simply delete this term. And we'll get that the deflection x is 4.154. So x equals 4.154 in inches. And there we have it.